Welcome back to the Deep Dive. Today, we are taking on something that's both incredibly complex and completely essential. We're mapping the invisible roadmap of electricity.
It's one of those things that's so fundamental to modern life, you almost never think about it.
Exactly. We're going to be peering deep into the architecture of, life itself, really. We'll be examining these truly massive, intricate systems that deliver reliable power to our homes, our businesses, all of our infrastructure, every single minute of every day.
And it's an exercise in both scale and precision. We're focusing today specifically on how major utility companies manage their entire supply chains.
Right.
I mean, everything from the moment they sign a contract for a fuel source to the moment you flip a switch. And along with that, we'll look at the very precise efficiency metrics they use.
And the constant battle they're fighting.
A constant high-stakes battle against losing power before it even gets to you, the consumer.
So that is our mission for you today. We are taking the diverse sources you shared with us and providing a really highly detailed, organized walkthrough. If you want the shortcut to understanding the nuts and bolts of energy logistics, the financial side, the technical, the logistical, we're going to deliver that deep dive.
And it's not just about making power. It's about managing a unique and a very volatile resource.
And I think that volatility is probably the best place to start. It's what makes this industry so different from almost any other.
It really is. For most of us, I mean, the electricity supply is just an invisible given. But behind that switch is a staggering operational challenge. The core difficulty of electricity, this unique product, is that it cannot be easily stored, not in massive grid-scale quantities anyway.
Right, you can't inventory a gigawatt. It's not like Amazon stocking books in a warehouse.
Precisely. When, a factory powers up its machinery or when millions of homes simultaneously crank up the air conditioning on a 100-degree day, that corresponding power has to be generated and consumed instantly. This absolute requirement for instantaneous synchronization makes the entire planning process, the logistics, the efficiency, it makes it all absolutely critical. If there's a breakdown anywhere in that supply chain, a delayed fuel ship, a failed transmission line, the whole system risks collapse.
So they have to be masters of prediction.
Of prediction and synchronization, yes.
Okay, let's unpack this then. Starting with the most fundamental definition. What does a supply chain even look like when your product basically evaporates the moment it's created?
That's the perfect question. When we define a supply chain, we're really looking at the total roadmap of how value is created and delivered, how it moves from its point of origin to its final point of consumption.
And that applies to any industry, right? Not just energy.
Any industry at all. Whether you're manufacturing cars or generating power, there are three core elements that have to flow simultaneously and synchronously for the system to work.
And a breakdown in any one of those three can just halt the entire process.
It can, yes.
Okay, so we're moving beyond just the physical product here. What are these three essential flows?
Okay, so there are the product flow, the information flow, and the financial flow.
Product, information, financial. Let's start with the product flow. That seems like the most obvious one.
It is. The product flow is the physical movement of goods. For a utility, this means a few different things. It's the movement of raw fuel, coal, oil, gas into the power plant. It's the movement of critical spare parts into the warehouse. And then ultimately, it's that non-storable, instantaneous flow of electrical current through the grid.
So if the fuel doesn't arrive, or the current can't actually be transmitted efficiently, the product flow just stops.
It stops. Which brings us to the need for coordination.
And that's where the information flow comes in.
That's where the information flow becomes absolutely essential. This is the transmission of all the critical data you need to keep the entire operation aligned. We're talking about demand forecasts, real-time data on how much power the grid needs right now, and how much it's going to need in, say, 3 hours.
So it's not just physical stuff, it's data. Delivery statuses, maintenance schedules.
All of it. Transformer capacity readings, billing data. Without a robust, instantaneous information flow, the whole system is, it's flying blind. Synchronization becomes impossible.
It's the nervous system of the grid. If that nervous system fails, the physical body, the product flow, it just can't respond to threats or demands.
That is an excellent analogy. And finally, you have the engine that powers the whole machine, which is the financial flow.
The money.
The money. This covers everything from managing credit terms with massive international fuel suppliers to payment schedules and, of course, the eventual collection of revenue from you, the end user. In the utility context, the financial flow is the collected revenue that ultimately pays for the next cycle of fuel and parts.
That interdependency is fascinating. If the financial flow stops, if customers don't pay their bills, for example, then the utility literally can't afford to execute that sourcing phase.
Which means the product flow, the power itself, will eventually stop. The system is immediately and incredibly circular. It's highly sensitive to any kind of external shock.
Right. Which is so different from a traditional supply
Oh,
chain.
completely. In a traditional supply chain, let's say you're producing and selling a physical widget, you have buffering capacity, you have inventory.
Hmm.
Suppliers provide raw materials, they're used in production, which produces finished goods.
Mm.
And those finished goods can sit in a warehouse. They can be distributed to retailers, sold to customers. You can afford a temporary financial lag because you have inventory you can sell in the meantime.
But the utility model, as we've established, has no significant finished goods inventory. You can't just warehouse megawatts.
Yeah, I can't.
So that traditional buffered supply chain structure,
Yeah.
it just doesn't apply. The utility supply chain is all about proactive prediction and synchronization.
Precisely. Because the product can't be stored, the utility model is fundamentally driven by these meticulous planning steps that have to synchronize supply with instantaneous demand. Our sources highlighted 5 essential planning steps for utility operations. The BPDB structure was a good example of this. This is where the logistics really shift from managing physical goods to managing abstract prediction and timing.
Let's dive into those planning steps then, because this really feels like the foundation of operational reliability. Where do they start?
Well, you start with demand planning. Since storage isn't an option, the utility's #1 job is to accurately forecast how much product is needed and, just as importantly, when. This prediction has to be highly granular, not just total daily demand, but the hourly peaks and valleys. This accurate forecast is the trigger for everything that comes after.
And once that demand is forecast, they have to go get the inputs to make it.
That's step 2, supply planning. This determines how to source the raw materials, the fuel, to meet that specific forecasted demand. It involves, long-term contracts for baseload fuels like gas or coal, and then shorter-term, often much more expensive contracts for peak load fuels like diesel or furnace oil.
So knowing the supply you need leads you right into scheduling the manufacturing, or in this case, the generation.
That's production planning. And this is the scheduling of the conversion of those raw materials into finished electrical energy. This phase requires some really sophisticated optimization software to decide which power plants run.
The base load versus the peak load plants.
Exactly. For how long, at what optimal efficiency. Always aiming to meet demand at the lowest possible cost while minimizing what we call the heat rate, which we'll get into later.
Okay, so the power's been generated. Now it needs a clear, reliable path to the consumer.
Which requires logistics planning. This is where you design the sophisticated transportation and delivery network. For a utility, this means ensuring the high-voltage transmission grid, which is often managed by a separate entity like PGCB, and the final low-voltage distribution network are operational, secure, and ready to handle that predicted load without excessive technical loss.
And the final piece, even for a non-storable product, is still inventory, but the focus is different.
Yes, inventory planning. Since they can't inventory the electricity itself, they focus on 2 critical buffer stocks: fuel and spare parts. This involves deciding how much of a fuel buffer to hold in case of supply chain interruptions, and crucially, how many expensive spare parts for turbines, generators, transformers to hold against an unexpected equipment failure.
Kind of a balancing act.
A huge one. Too little means a high risk of an outage. Too much means you have millions in capital just sitting idle. Effective management of these 5 steps is what transforms that prediction of demand into the reality of 247 power.
So let's take those 5 planning steps and see how they translate into the practical physical flow of the energy utility supply chain. The BPDB example you mentioned is a great case study for this. It really shows that circular nature of the business, where the final financial act feeds directly back into the initial prediction.
It does. And the cycle starts not with a physical action, but with intelligence. Phase 1, demand forecasting, is the trigger. BPDB planners are analyzing not just last year's data, but minute-by-minute historical consumption patterns. Then they overlay this with all sorts of external variables, economic growth forecasts, major industrial projects coming online, and, most critically, weather predictions.
And they're not just predicting the average temperature, right? They need to predict the timing of the absolute peak heat.
Exactly. In hot climates, air conditioning drives these massive peak loads. They have to predict the precise megawatt demand required for the national grid during the highest stress moments, which are often those hot summer evenings.
And that number is everything.
It is the single most foundational number. Every subsequent dollar spent on fuel is based on the volume determined right there. If that forecast is wrong, the utility either experiences rolling blackouts,
If they underforecast it.
or they waste billions on excess fuel and inefficient generation if they overforecasted. There's very little room for error.
So once that massive megawatt demand is forecast, the utility has to go secure the means to meet it. That brings us to phase 2, sourcing.
This is where the utility enters the global commodity markets. Based on that forecast, procurement is immediately planned for the necessary primary energy sources: furnace oil, diesel, coal, and gas. For an entity like BPDB, which often relies heavily on imported furnace oil and LNG, that's liquefied natural gas, this sourcing phase is incredibly sensitive to volatile international prices and, frankly, geopolitics.
So their supply planning is just completely intertwined with global market risk.
Absolutely. Sourcing involves major multi-year contracting with national entities like Petrobangla for domestic gas supply, or securing international agreements for imported coal and oil. And this phase also includes sourcing essential, often multi-million-dollar turbine spare parts.
Those could have really long lead times, I imagine.
Very long, so they have to ensure that supply chain for maintenance is secured well in advance of any potential need.
Okay, so with the fuel secured and the parts on hand, we move to the actual production of electricity. Phase 3, generation. This sounds like it requires some complex operational scheduling.
It's a huge optimization puzzle. The scheduling differentiates between two main types of plants. You have your baseload plants. These are typically the most cost-effective and efficient, often large coal or modern gas plants, and they're designed to run 24/7 to provide the minimum required power for the grid.
And then you have the backups.
Then you have the peak load plants. These are often less efficient or more expensive, sometimes older diesel plants, and they're only switched on during those high-demand periods that were predicted back in phase 1.
So the challenge is to schedule them just right.
The optimization challenge is scheduling these units to meet demand instantly while minimizing the very high marginal cost that's associated with firing up an expensive peak load unit. In this phase, the raw fuel is finally converted into electrical energy at these generation units.
Now, once that current is created, you have to maintain its integrity while it travels, sometimes hundreds of miles. So that's phase 4, transmission and distribution, the delivery network.
And this phase represents a significant logistical challenge of movement. It starts with transmission, that's sending the generated high-voltage power over the large primary lines to the central grid. This is often managed by a separate government entity, like PGCB in the context we're discussing.
And they use high voltage for a specific reason.
Yes, high voltage is used specifically to minimize technical loss over long distances. It's a matter of physics.
And then the utility takes over again for that critical final mile.
That's the distribution stage. This involves stepping down that high voltage multiple times via numerous substations and distribution transformers. This final stage is the delivery of the electricity to the residential, commercial, and industrial end users via the utility's own specific network. And as we're going to discuss later, this low-voltage network is the most complex, the most loss-prone, and the most labor-intensive part of the entire supply chain.
And finally, we get to the essential financial component, the part that has to succeed to ensure the entire cycle can repeat itself.
That is phase 5, revenue collection. This involves meter reading, accurate billing, and most importantly, actually collecting the billed funds. This is what closes the financial loop. If this phase is inefficient, if what we call the collection-to-bill ratio is low, the utility lacks the necessary cash flow to execute phase 2, the sourcing phase, effectively.
So they can't buy fuel for the next cycle.
Exactly. The failure to collect revenue today directly causes power outages in the future.
It's clear that this whole process is incredibly interwoven. But how do the utility managers actually know if they're performing well, or if they're, hemorrhaging money or efficiency somewhere in that 5-phase cycle? This is where the key performance indicators, the KPIs, come in.
The KPIs are the utility's life signs. They really are. They provide an objective measure of operational health, and they allow management to pinpoint specific weak spots, whether that's a slow-moving inventory, an inefficient generator, or a failure in revenue protection. We can categorize these metrics across the 4 major functions of the physical supply chain.
Let's start at the beginning of the flow then, sourcing and inventory. The key goal here seems to be guaranteeing that your inputs are available, but without letting capital just sit there idle.
That's the balance. The first critical metric here is the fuel availability index. This is a measure of the required operational hours versus the actual hours the necessary fuels, gas, oil, coal, were available precisely at the moment the plants needed them. The target, especially for those baseload plants, is nearly 100%.
And if that index drops even a little bit, what's the immediate consequence?
Well, let's say a baseload plant is expecting cheap natural gas, but the delivery is delayed. The utility has to make a choice, and fast. They either shut down the plant or they switch to a high-cost, high-emission backup fuel like diesel or expensive furnace oil, often bought on the spot market.
Which must be incredibly expensive.
It can dramatically increase the cost of supply for that hour or that day. It destabilizes the entire production plan and ultimately raises costs for the consumer. So achieving 100% availability means the sourcing phase successfully synchronized fuel arrival with the generation schedule.
The second key KPI in this area relates to the non-fuel inputs, the inventory turnover ratio for spare parts. We talked about the risk of dead stock.
Right. This metric measures how often specialized, high-cost capital items, things like turbine blades, generator windings, specialized circuit breakers, are used and replaced over a set accounting period. A high turnover is generally a good thing. It signifies efficient use of your stock.
But the utility context complicates that a bit, doesn't it? You need a buffer of these very expensive items, even if you don't use them frequently.
Absolutely. And that's the nuance. A low inventory turnover ratio signals that capital is tied up in dead stock. It's expensive, specialized parts just sitting unused in a warehouse. While a utility has to have a buffer for high-impact parts, an excessively low ratio means money that could be used for fuel purchases or grid upgrades or debt servicing is just idling in static inventory.
So it's a delicate management challenge.
It's finding that perfect balance between minimizing tied-up capital and ensuring immediate availability to prevent an unplanned week-long outage. That's what this KPI reveals.
Okay, let's move on to the actual physical transformation phase, the generation KPIs. This is where engineering and economics really collide, especially when we look at something called the heat rate.
The heat rate is perhaps the single most crucial efficiency metric in generation. It's the measure of the thermal energy input, that's in BTUs or joules required to generate just one single unit of electrical energy, 1 kilowatt hour. It's essentially the inverse measure of efficiency.
So you want that number to be as low as humanly possible. What are the factors that cause a high heat rate?
A high heat rate typically points to older plant technology, older boilers, turbines that haven't been modernized, or just poor operational maintenance. For example, excessive scaling or fouling in the heat exchange systems reduces your thermal transfer efficiency.
So every extra bit of fuel needed is just wasted money.
Every extra BTU of fuel needed to produce that kilowatt is wasted money. It directly translates operational inefficiency into massive fuel cost implications, which again is the utility's largest single expense. Monitoring this KPI allows managers to identify which specific plants need modernization or retirement or an immediate maintenance overhaul.
And tied very closely to the heat rate, we have the measure of reliability, the plant availability factor.
Yes. This is a percentage that reflects the amount of time a power plant is actually ready and capable of generating power versus the total time it exists. A high availability factor, say, above 90% means the plant is robust, it's well maintained, and it suffers minimal unplanned downtime due to mechanical failure.
And if that availability factor is low, what kind of pressure does that put on the entire system?
A low availability factor forces the utility to rely more heavily on those less efficient, more expensive peak load plants. Or worse, they might have to purchase electricity from emergency or short-term spot markets at a premium.
Can we put some numbers on that?
Sure. Let's consider the cost difference. A modern, well-maintained baseload plant might produce power at, say, 6 cents per kilowatt hour. A peak load unit running on high-cost diesel might produce it at 15 cents per kilowatt hour.
More than double.
Right. So if low availability forces you to use the expensive option for thousands of megawatt hours, the financial hemorrhage is immediate and substantial.
Next, we arrive at the distribution and delivery side. And here, one KPI really stands out as fundamentally critical for a utility's health. System loss.
System loss is the measure of the difference between the energy you generated back in Phase 3 and the energy you actually billed to customers in Phase 5. It is quite literally where power simply vanishes from the ledger.
And how do they calculate that?
The calculation is straightforward. You take the energy generated, subtract the energy sold, divide that by the energy generated, and multiply by 100 to get a percentage.
So if a utility generates 100 units of power but only sells 88, the system loss is 12%. That percentage might not sound huge to some, But what does a 1% system loss reduction actually mean in real-world financial terms for a large utility?
It's massive. For a utility serving a major urban center, a single 1% reduction in system loss can translate into hundreds of millions of dollars annually. That 1% is power. The utility no longer has to pay fuel costs for, but which it can now bill for. It's pure leakage.
So the target is always to get that number down.
The target for most successful utilities is continual reduction. They're always aiming to move from historical double-digit figures down into the low single digits. If a utility has a 12% loss, it means they're effectively paying for 12% more fuel and generation capacity than they're actually getting paid for. It's a critical indicator of both financial leakage and grid inefficiency.
Beyond just the energy loss, there's the customer experience, which is measured by two key indices related to reliability and outages.
These are SAIPD and SAIFI. We look at SAIDI, which is the System Average Interruption Duration Index. This focuses on time. It measures the total duration of outages experienced by the average customer over a period, usually measured in minutes per year.
So it tells you when the power goes out, how long does it typically stay out?
Precisely. A low number indicates fast response and repair times, and then you have its partner, SAIFI.
Which measures how often it happens.
Exactly. SAI, the System Average Interruption Frequency Index, measures how often the average customer experiences an outage in a year. A low SAI-FI score means the grid architecture is highly resilient and doesn't suffer frequent system-wide failures. These two metrics, when you take them together, capture the tangible impact of grid health on daily life. They're a core measure of service quality.
Okay, so finally, we close the loop with the financial KPIs. These measure if the utility is actually financially sustainable, ensuring they can fund the next operational cycle. The first one seems absolutely vital: the collection-to-bill ratio, or CB ratio.
This is the percentage of billed revenue that is actually collected from customers. The goal is to be as close to 100% as possible. If that ratio is low, if a significant portion of billed revenue remains unpaid past the due date, the utility suffers severe working capital constraints.
And as we said earlier, that directly impacts their ability to operate.
It does. They can't purchase the necessary fuel and parts for the next cycle. It leads to a financial crisis that eventually manifests as physical instability on the grid.
But that collection challenge is often compounded by the next metric, which is the comparison of cost versus price.
That's the cost of supply per unit. This is the total cost required to generate, transmit, and deliver 1 kilowatt hour versus the price at which the utility is legally allowed to sell that unit of electricity.
And in many places, that selling price isn't set by the market.
That's the key complication. In many contexts, like the BPDB example, utilities are often state-owned or heavily regulated. The selling price is a political decision, not a market one.
Which is where the analysis gets tricky. The source material hints that if the cost of supply exceeds the selling price, the utility is operating at a totally unsustainable loss.
Precisely. If, due to high fuel prices or high system loss, the cost to deliver a kilowatt-hour is, let's say, 10 cents, but the regulated selling price is only 8 cents, the utility is fiscally unsustainable. It can only survive through government subsidies or by accumulating massive debt. This KPI is essential for regulators and governments to understand the true financial health and subsidy requirements of the entire sector.
You know, here's where it gets really interesting for me. Because all those KPIs we just discussed, especially system loss and plant availability, are currently being applied to a grid structure that is fundamentally changing. The physical architecture of how power moves is evolving. It's shifting from a single, centralized system to a more complex, distributed model.
That's right. The historical model, the legacy model, has been the backbone of industrial society for a century. But it has some very defined limitations when it comes to efficiency, security, and resilience. This is the centralized generation system.
Can you describe that standard legacy model for us, and maybe touch on what makes it fragile?
Sure. It's characterized by these massive large-scale generation units, which are located far from the consumption centers. Think of huge power plants built near fuel sources like a coal mine or a major river for cooling.
So the power has to travel a long way.
A very long way. The power flows unidirectionally. It travels first through a high-voltage transmission network over hundreds of miles. Then that power is stepped down at substations and routed through the distribution network before it finally reaches the end consumers. The major vulnerability here is the scale. If one massive plant fails, or a single high-voltage transmission line is compromised, huge portions of the system can fail catastrophically.
It's a classic hub-and-spoke model, very top-down. But the distributed generation system is changing that entire paradigm. It's making the flow multidirectional and, at least in theory, more resilient.
It's a radical departure. This evolving model is defined by smaller, more dispersed generation sources that are integrated directly into the distribution grid, often much closer to where the demand actually is. This decentralization fundamentally changes how the grid has to be managed.
What kind of sources are we talking about here? What's feeding into this new complex structure?
Well, they're highly varied. You still have the existing large-scale generation units, but they're now supplemented by rapidly deployable sources like large-scale photovoltaic plants, solar farms, and wind turbines, and increasingly, local power sources.
Like what?
Things like localized combined heat and power plants that might serve a local industrial complex, and even domestic consumers with their own PV systems. Rooftop solar panels who, when they're generating excess power, can feed that power back into the distribution network.
With power coming in from so many different intermittent sources, sun, wind, local private entities, it seems like system synchronization would be a staggering logistical challenge, just ensuring the quality control alone.
That's absolutely right, and it requires entirely new architecture. Since solar and wind are intermittent, two crucial elements have to be added to the system. First, storage units are essential buffers. Think grid-scale batteries. They manage the volatility of these sources before the power is distributed. They charge up when the sun is shining or the wind is blowing, and they can discharge instantly when needed.
And the second element?
The second is a sophisticated central control system. The entire heterogeneous system has to be managed, often relying on advanced AI and smart grid technology to ensure all these disparate generation points are synchronized, balanced, and are maintaining voltage stability. The flow is no longer one way. It's a constant optimization of flow based on real-time generation and localized demand.
And alongside this huge shift in architecture, utilities are finding advanced ways to maximize the energy they produce from the fuel they burn. They're moving beyond just generating electricity. Our sources gave a really detailed look at some advanced efficiency concepts, specifically trigeneration and heat pumps.
Right. This moves efficiency beyond just the heat rate of the generator. It focuses on utilizing the unavoidable waste products. In a standard thermal generation, process burning fuel to make electricity, a significant amount of heat is an unavoidable byproduct. And that heat is often just vented away or cooled via massive towers, which represents a major energy loss.
So how does trigeneration capitalize on that wasted heat to dramatically improve the overall efficiency?
Trigeneration, which is also known as combined cooling, heat, and power, or CCHP, is all about thermodynamic optimization. Fuel enters a trigeneration unit. This unit produces electricity, that's the primary goal. But critically, it also captures the usable heat that would otherwise be wasted.
There are still losses, though.
Oh yes, there are still unavoidable thermodynamic losses. But by capturing that heat, the overall system efficiency can jump from a typical 40% for just electricity to maybe 80% or 85% total energy utilization.
So now you have electricity and you have this captured heat. The diagram then shows that the captured heat, along with some additional electricity, gets fed into a heat pump.
The heat pump is the final layer of this maximization. It uses the input heat and electricity to efficiently move thermal energy around. The heat pump then effectively outputs two highly useful services: cooling for air conditioning or refrigeration, and further usable heat for space heating or industrial processes.
So one unit of fuel is giving you three services.
Exactly. The net effect is that one initial input of fuel is providing three services: power, heating, and cooling, all while maximizing the utilization of the chemical energy that was inherent in the fuel. This is a vital concept for energy-intensive facilities like hospitals, universities, or industrial parks because it reduces their reliance on the external grid.
This detailed look at flow and architecture brings us right back to that single most critical KPI we discussed earlier: system loss. Whether the grid is centralized or distributed, battling loss is the financial and operational reality for every utility, and it requires a multifaceted approach.
System loss is the largest operational and financial vulnerability, and it's important to reiterate. This loss isn't just wasted energy, it's energy the utility paid fuel costs for but can never, ever bill a customer for. To combat this effectively, management has to apply two distinct parallel strategies.
Why two?
Because the loss originates from two fundamentally different sources.
So how do analysts definitively categorize the source of the leak?
They categorize it into technical loss and non-technical loss, which is also called commercial loss. Technical loss is the inevitable outcome of physics. It's the energy that's naturally lost as heat because of the electrical resistance in wires, conductors, and transformers. You can't eliminate it, but you can minimize it through infrastructure investment. We call that grid hardening.
And the other side is much more challenging, I'd imagine, because it involves human behavior.
That's the non-technical or commercial loss. This is the human factor. This is energy that is consumed but never billed due to human intervention. It could be meter bypassing, outright theft through illegal hookups, corruption among manual meter readers, or just simple estimation errors in billing. Addressing this requires legal action, policing, and sophisticated technological countermeasures. We call this revenue protection.
Okay, let's dive into strategy A, reducing technical loss or grid hardening. These are the major capital expenditures designed to physically improve the infrastructure. Where do you start?
The first, and often most expensive, is reconductoring. This is the process of replacing older, often thin wires, which have high electrical resistance, with newer, higher capacity conductors. These are typically made of better materials or simply have a larger cross-sectional area.
Why does a thicker wire reduce loss? Can you give us the physics behind that for the listener?
Sure, it relates directly to resistance. The resistance of a conductor, we'll call it R, is inversely proportional to its cross-sectional area, A. A basic principle of electrical engineering is that power lost as heat is calculated by the formula P equals I squared R. That's current squared times resistance.
So a bigger wire means less resistance.
A bigger wire means less resistance. By replacing older, thinner wires with conductors that have a larger cross-sectional area, you significantly reduce R. And a reduced R immediately results in less heat being generated for the same amount of current flowing through it. So you directly reduce the energy wasted as heat loss in the lines. It's a massive long-term investment, but it yields perpetual operational savings.
Transformers are also critical points of failure and waste, right?
Yeah. Absolutely. The second major action is transformer load management. Transformers step down voltage, but when they operate inefficiently or are severely overloaded, they heat up excessively and waste a significant amount of energy. So utilities have to use smart grid monitoring to identify these overloaded transformers, the ones operating beyond their peak efficiency curve, and either replace them with higher capacity units or redistribute the load in the surrounding area. An optimized transformer fleet can save a huge amount of technical loss.
Okay, next we have a solution that sounds highly technical, but you said is crucial for efficiency.
Yeah.
Installing capacitor banks. What are these for?
Capacitor bank installation is implemented at substations primarily to improve what's called the power factor. To put it simply, electrical current can be broken down into two components. Real power, which actually does the work. It runs your lights, spins motors, and reactive power.
And what does reactive power do?
Well, it's necessary to establish the magnetic fields in motors and transformers, but it essentially just sloshes back and forth the lines. It doesn't do any useful work.
But it still contributes to heat loss, even though it's not doing any actual work.
Exactly. When the power factor is low, it means there is excessive reactive power flowing, which means the conductors are carrying more total current than necessary to deliver the real power. And since heat loss, that I squared R formula depends on the total current, excessive reactive power unnecessarily increases technical loss and heating in the wires. Capacitor banks inject the necessary reactive power locally into the system.
So it doesn't have to travel as far.
Right. It prevents that wasted power from traveling long distances across the utilities wires, and that leads to much cleaner, more efficient transmission.
And the final piece of this grid hardening strategy is about manipulating the structure of the lines themselves, shortening the low voltage lines.
This is a design philosophy, and it's based on physics. High voltage lines inherently lose less power over distance than low voltage, or LV, lines. This is because high voltage allows the system to transmit the same amount of power, but with much less current. And as we know from I squared R, that exponentially reduces loss. So the strategy is to move the high voltage closer to the consumer. We call this optimizing the substation placement. And by doing so, you keep the final, loss-prone, low-voltage lines as short as physically possible. You're minimizing the distance over which power is guaranteed to be wasted.
That covers the physics side. Now, for the really challenging human side, strategy B, reducing commercial loss or revenue protection. This sounds like it requires vigilance, technology, and often confrontation.
It does. This strategy targets theft, fraud, and administrative errors. And the sources identify one particular tool as being the most revolutionary and effective in this arsenal: 100% prepaid metering.
How does just changing the payment structure so dramatically reduce commercial loss?
Well, it addresses the root causes of non-technical loss all at once. First, it eliminates the administrative loss caused by human error or corruption in manual meter reading and billing estimation. The usage is digitally recorded and paid for upfront.
And the second reason.
Second, and critically, it's the most effective deterrent against theft. The prepaid meters are advanced digital devices. They are inherently designed to shut down if usage is detected without a corresponding payment buffer. This makes meter bypassing and illegal hookups much, much harder and easier to detect than with traditional analog meters.
It just eliminates the incentive and the opportunity for manipulating the billing process because payment is mandatory before you can use the power.
Exactly. But, technology is never foolproof against determined organized theft, so utilities can't rely only on the meters. They have to maintain a physical deterrent.
And that's where the anti-theft drafts come in.
Yes. These are regular, unannounced vigilance team raids in identified high-loss zones. These operations are essential to physically detect and disrupt illegal hookups, issue fines, and prosecute repeat offenders. This requires a dedicated, well-funded revenue protection unit.
And what about addressing internal corruption or just simple human error in reading and recording usage, especially during a transition period?
That's where digital integration and automation become paramount. By automating the entire process from meter reading to data transfer to calculation and finally to billing, the utility removes the opportunity for human error or corruption. You take away the chance for manual meter readers to be bribed to underestimate consumption. Automation creates a verifiable data trail that is very hard to tamper with and that dramatically boosts the CB ratio.
Finally, in the most challenging environments, I'm thinking dense urban areas where cables are really accessible. Sometimes the physical solution is the most extreme one, burying the cables.
Underground cabling. In dense urban environments where cables are often strung across rooftops or along poles, making illegal hooking trivial, physically moving those cables underground makes physical access for tampering nearly impossible without major excavation. It's a massive infrastructure investment, but it's designed to provide robust revenue protection in high-risk zones. It effectively hardens the system against physical commercial intrusion, though it does come with very high upfront costs and complicates future maintenance.
This has been a deeply detailed look at a truly complicated machine, from those 5 phases of utility planning that start with a prediction to the 9 diagnostic KPIs that act as the system's nervous system, and then finally this 2-pronged attack on system loss. It really all comes down to a central high-stakes balancing act.
Absolutely. The utility's job is a continuous high-wire synchronization act. They have to instantly match this highly volatile, fluctuating demand with supply, all while battling the twin enemies of physics represented by technical loss, which requires billions in grid hardening and human factors, embodied by commercial loss, which requires intense revenue protection. Every single decision about sourcing fuel or scheduling a power plant or replacing a piece of cable is fundamentally aimed at making sure that instantaneous need for power is met reliably and sustainably without crashing the system financially or physically.
So what does this all mean for you? Well, it means that every single time you flip a switch, the power delivered to you has been the subject of this intensive planning, measurement, and strategies designed to claw back every possible kilowatt hour from the jaws of both physics and human intervention. The cost and the reliability of that power are directly tied to how well the utility manages these complex interconnected flows.
And as we move toward this era of distributed generation, the system gains resilience, but it introduces a whole new level of complexity into that financial flow. We've talked about how commercial loss theft fraud is typically managed by locking down the final delivery stage to millions of end users. But consider how the shift to distributed generation complicates this battle. Instead of one central generator selling power to millions of passive customers, you now have thousands of small generators, businesses, homes with solar that can potentially sell power back to the grid. They become commercial actors themselves. This structural change forces utilities to rethink revenue protection entirely because the points of financial vulnerability are no longer just where power leaves the utility, but potentially where it enters from hundreds of independent, less regulated sources. This challenge, the challenge of protecting revenue in a dynamic, multi-directional grid, is really the next frontier of utility supply chain management.